Your lawn, untouched by rain, still wakes up drenched. It's a silent, everyday mystery. Every morning, millions of us step outside or glance out a window and see it. A glistening carpet of tiny water droplets coating every blade of grass, every spiderweb, every fallen leaf. Yet the night was clear, the sky was star-studded, and not a single drop of rain fell. How does this happen? This isn't just some charming natural phenomenon. It's a testament to the invisible forces constantly at play around us. It's a precise dance between temperature, humidity, and the very air we breathe. A dance that happens every clear night, right in your backyard. Understanding dew isn't just about satisfying a curious mind. It helps us grasp the delicate balance of our local ecosystems, influences agriculture, and even plays a surprising role in historical events and ancient navigation. It's far more significant than just wet shoes. To truly appreciate dew, we first need to understand humidity. Imagine the air around you as a sponge, capable of holding a certain amount of water vapor. Warm air is like a big, thirsty sponge. It can hold a lot of water. Cold air, however, is a much smaller sponge, quickly saturated. During the day, the sun heats the Earth's surface, and that warmth radiates into the air, allowing it to hold more moisture. This water often evaporates from lakes, rivers, and even the plants themselves. It floats around, invisible as water vapor. But as evening approaches, especially on a clear night, something crucial happens. The Earth's surface, no longer warmed by the sun, begins to radiate its heat back into space. This is called radiative cooling. Think of it like a blanket being slowly pulled away. Objects on the ground, like blades of grass, car roofs, and even park benches, cool down much faster than the air just a few feet above them. They have less mass, less thermal inertia. This difference in cooling rates is key to our dew mystery. As these surfaces cool, the layer of air directly touching them also cools. Remember our sponge analogy. As this thin layer of air gets colder, its capacity to hold water vapor shrinks dramatically. It reaches its saturation point, known as the dew point. Once the air temperature drops to the dew point, that little sponge can't hold any more water. So what happens to the excess water vapor? It has to go somewhere. It condenses, changing from an invisible gas into visible liquid water. And where does it condense? Right onto those cool surfaces. The grass, the leaves, the car windshield. These surfaces act as perfect nucleation sites, tiny platforms for water molecules to gather and form those familiar sparkling droplets. This process isn't unique to Earth. Scientists observe similar phenomena on other planets and moons where atmospheric conditions allow for condensation. It's a universal principle of physics, playing out in countless ways across the cosmos. Now you might be thinking, what about fog? Fog is essentially dew that forms in the air itself, rather than on a surface. When a large body of air cools to its dew point, and there are enough microscopic particles for water to condense onto, we get fog. So a clear night is actually essential for heavy dew. Clouds, you see, act like a blanket. They trap the heat radiating from the Earth, preventing the surface from cooling down enough to reach the dew point. That's why cloudy nights are often dew-free. Wind also plays a role. A gentle breeze can actually enhance dew formation by bringing more humid air into contact with the cool surfaces. But too much wind, a strong gust, can disrupt the cool air layer near the ground, hindering condensation. The amount of dew can vary greatly depending on location and climate. Coastal areas often experience heavier dew due to higher ambient humidity. Deserts, surprisingly, can also experience significant dew, providing a crucial water source for plants and animals. Consider the Namib desert beetle, for instance. It has specialized grooves on its back that collect condensed fog and dew, funneling the precious water directly to its mouth. A stunning example of adaptation to a seemingly waterless environment. Historically, dew has been both a blessing and a mystery. Ancient civilizations observed it, often attributing it to divine tears or mystical origins. Farmers, even today, rely on dew as a supplementary water source for their crops, especially in arid regions. For early navigators, understanding dew formation was a matter of survival. The presence or absence of dew could indicate upcoming weather changes or even the proximity to land, as coastal areas often have different dew patterns. Even in modern times, dew plays a role in various technologies. Researchers are developing dew harvesting systems, inspired by the Namib beetle, to collect potable water in regions facing water scarcity. Imagine buildings designed to pull water right from the air. So the next time you see your lawn glistening in the morning sun, remember it's not just random moisture. It's a perfect miniature science experiment playing out, a symphony of physics and thermodynamics orchestrated by the subtle shifts of night and day. It's a reminder that even the most ordinary parts of our daily lives are packed with extraordinary processes, waiting for us to observe, to question, and to understand. The world is full of these quiet wonders, if only we take a moment to look closely. From the vastness of the cosmos to the single blade of grass in your backyard, the same fundamental laws of nature are at work, creating beauty, sustaining life, and offering endless opportunities for discovery. Next, let's uncover the surprising reason why some clouds are white and others are dark.